Good morning. My name is Jayashree Mutugar, JFGC Hulkoti, session number 19, BSc third semester Physics. First, we discuss the Ramsden's and Huygens eyepiece. Both are the differences. Ramsden's eyepiece. Ramsden's eyepiece consist of two plano-convex lenses separated by the about 2 divided by 3 f. The final image is formed at infinity. The function of the field lens is to deviate toward the axis those rays which would otherwise miss the eye lens. This is the increased field of views. Let the focal length of the equivalent lens 1 divided by f equals to 1 divided by f1 plus of 1 divided by f2 minus of d divided by f1 into f2. This value we can put the d and 1 divided by f equals to 3 divided by 4 ef. The equivalent of the length of the field lens at the distance alpha from the alpha equals to f into d divided by f2. This answer is f divided by 2. The equivalent lens is the between the field lens and the eye lens. Merits and demerits of the Ramsden's eyepiece. The field of view of the eyepiece is fairly wide. It is not entirely free from the chromatic aberration since the distance between the two lenses is not equal to half the sum of their focal length. However, chromatic aberration is minimized by using an achromatic combination both for the field lens and the eye lens. Spherical aberration is minimized by using two plano-convex lenses, Ramsden's eyepiece. It is practically in all instruments where measurements of the size of the final image are to be made. Huygens eyepiece, both are the two lenses are separated by the distance equal to the average of their focal length. The function of the field lens is divided inwards those rays which would otherwise have missed the eye lens, thus increasing the field of view. Huygens eyepiece reduces longitudinal chromatic aberration. The focal length of the f1 and f2 place the d distance from 1 divided by capital F equals to 1 divided by f1 plus 1 divided by f2 minus of d divided by f1 into f2. The dispersive power of the Huygens eyepiece. 1 divided by f1 plus of 1 divided by f2 minus of d into f1 plus f2 divided by f1 into f2. Achromatism, d equals to f1 plus f2 divided by 2. Huygens eyepiece merits and demerits. Huygens eyepiece is fully free from chromatic aberration because the distance between the lens is equal to the half the sum of their focal lengths. Spherical aberration is also minimum because the distance between the two lenses is equal to difference of their focal length. Next point, the field of view of these eyepiece is smaller than that of a Ramsden's eyepiece. Both the comparison, Ramsden's eyepiece and Huygens eyepiece. Ramsden's eyepiece is a positive eyepiece. Huygens eyepiece is a negative eyepiece. Ramsden's eyepiece, the image formed by the objective lies in front of the field lens, therefore crosswire can be used. But Huygens eyepiece, crosswire cannot be used. Next point, Ramsden's eyepiece. The condition for minimum spherical aberration is not satisfied, but by spreading the deviation over focus 4 surfaces, spherical aberration is minimized. The condition for minimum spherical aberration is satisfied. Third one, Ramsden's. It does not satisfy the condition for achromatism but can be made achromatic by using an achromatic doublet as the eye lens. But Huygens eyepiece satisfies the condition for achromatism. Ramsden's. It is achromatic for only two choose colors. Achromatic for all colors. Ramsden's. The other types of aberrations are better eliminate coma is absent and distortion is 5% higher. The other type of aberrations like distortion are not eliminated. The eye clearance is 5% higher, but Huygens the eye clearance is too small and less comfortable. Its power is positive in Ramsden's and both the Huygens also. The two principal planes are crossed. Ramsden's eyepiece also same and Huygens eyepiece also same. It can be used as a simple microscope because the first principal plane lies to the left of the field lens and the focal plane is real. It can be used as a simple microscope because the first focal plane lies to the right of the field lens and the focal plane is virtual. The noodle point coincide with the principal point. The noodle points coincide with the principal points. Some of the numerical problem we can see here. First one, calculate the equivalent focal length for achromatic combination of two thin lenses of focal length 1 meter and 0.4 meter respectively. Separated by the distance, assume that both the lenses are of the same material. F1 is equals to 1 meter, F2 equals to 0.4 meter, D equals to F1 plus F2 divided by 2. D is equals to distance 0.17 meter. Focal length formula 1 divided by F equals to 1 divided by F1 plus 1 divided by F2. Value is F equals to 0.05 meters. Two thin lenses of the same material with the focal length 0.08 meter and 0.04 meter are placed at a certain distance apart. Calculate the distance between the lenses if they form an achromatic combination. Also, calculate the equivalent focal length. Given value of the focal length f1 equals to 0.08 meter and f2 equals to 0.04 meter. D the distance, D equals to 0.06 meter. 1 divided by f plus equals to 1 divided by f1 plus 1 divided by f2. Value here put the 1 divided by 0.08 and 1 divided by 0.04 meter equals to 37.5 meters. Next question. The focal length of a thin double convex lens are 1 meter and 0.96 meter for the red and violet color respectively. Find the longitudinal chromatic aberrations. Given values, Fr equals to 1 meter red color, F focal length of violet color is 0.96 meter. Fr minus Fv calculating. Longitudinal chromatic aberration Fr minus Fv equals to 1 minus 0.96 equals to 0.04 meter. Next question. The focal length of two lenses forming an chromatic doublet are 1.2 meter and 1.8 meter respectively. What is the ratio of their dispersive power? Given value are F1 and F2 are F1 value we put here 1.2 meter and F2 value is 0.8 meter. Omega 1 and omega 2 by omega 2 value equals to minus F1 divided by F2. 1.2 divided by 0.8 value is minus 3 divided by 4. In concluding with the positively ratio omega 1 ratio omega 2 equals to 3 is to 2. Thank you.